Hey guys, I had a request to explain to you how Slater's rules work for figuring out the effective nuclear charge on an electron in an atom. These are three kinds of questions you could see. Find the effective nuclear charge for a 3D electron in iron, or a 5s electron in strontium, or a 1s electron in neodymium. If you're given the electron you need the effective nuclear charge for and the atom, you're going to be able to figure out what that effective nuclear charge is. Now this is the actual amount of positive charge that the electron sees. If you take a look here at strontium, it's element number 38, which means there are 38 protons in the center. But an electron far away from the nucleus won't see all 38 at once because there are other electrons blocking its view. Maybe it'll only see the equivalent of 11 or 15 or 3 or something. It'll see less than 38, and that amount that it actually sees is the effective nuclear charge. So, how do you find the effective nuclear charge with Slater's rules? Step 1, write the electron configuration for the atom itself. I'm going to do that right now for iron. According to the periodic table here, iron is element number 26. So, according to my order of filling, that means it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. 2, 2, 10, 12, 18, 20, 26 electrons. Why does 4s come before 3d? Because of the order of filling. If you don't know what I'm talking about, Google order of filling. Okay, step 2. Rearrange all of these from the highest to lowest n. Notice that this 4 came before this 3. We're going to switch those back only for the purposes of Slater's rules. And we're going to group s and p's together, and everything else is going to stay separate. Here's what I mean. In the first shell, we have 1s2. Check. In the second shell, we have 2s2, 2p6. I'm going to keep those together because it's an s and a p. We'll group those together. In the third shell, we have 3s2, 3p6. Keep those grouped together because it's s and p. Remember, we're going from lowest to highest n. So, 3d6 comes next, and 4s2. Okay, so everything's separate, goes from lowest to highest n, and only the s's and p's with the same n's are grouped. Check. Next, you have to figure out which electron you're calculating the ZEFF, or effective nuclear charge, for. In this case, it's a 3D electron. And depending on what kind of electron you're doing it for, you have different rules, I'm afraid. For a D or F electron, you're going to add up 0.35 for every electron in the same group, and 1 for every electron in a lower group. 0.35 in the same group, 1 in every lower group. Here's what I mean. We're doing it for a 3D electron. How many other electrons are in 3D? 5 of them. There are 6 total. We're doing this for one of them. There are 5 other electrons. We deduct 0.35 for every single one of those. And we deduct 1 for every electron in any other lower group. So there's 8 here, so we're going to subtract 1 8 times. Here, there's 8 electrons. Subtract it 8 times. There's 2 electrons here. Subtract it 8 times. Add all of these together. 2 plus 8 plus 8 plus 5 times 0.35. That's, no, I don't have my calculator with me. Yes, I do. Bam. On. 2 plus 8 plus 8 plus 5 times 0.35 gives me a total of 19.75. This is the total amount of shielding. Notice there's more shielding for electrons that are closer than the electron you're talking about. Finally, the final effective nuclear charge, you just take your atomic number 26 and subtract that shielding, 19.75, and you get your answer, 6.25. So, even though there are 26 protons at the center of an Fe atom, a 3D electron will only actually see 6.25 of them. That's important in terms of, well, how easy is it to remove the 3D electron? Well, if it was seeing 26 positive charges, it wouldn't want to go anywhere because it's really attracted to them. But it's really only seeing 6 positive charges, so it's probably easier than you think to remove a 3D electron. Okay, let's do this again for a 5s in strontium. Step 1, write an electron configuration. Well, strontium is element number, got my periodic table, strontium is element number 38. So I need 38 electrons, and I need my order of filling. Excuse me, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. That takes me to 38 electrons, I believe. 2 and 2, 10, 12, 18, 20, 38 electrons. Bam! Who's awesome? I am. Rearrange these from lowest to highest n. Group the s's and the p's. Here we go. 1s2 stays solo. 2s2, 2p6 gets grouped. 3s2, 3p6 gets grouped. 3d10, all the 3's first. 4s2, 4p6, s's and p's grouped. 5s2. Okay. And which electron are you calculating effective nuclear charge for? For an s electron, you follow these rules. You add up 0.35 for each electron in the same group. Same rule as before. But here, you're also going to add up 0.85 for each electron one shell lower than the one you're talking about, and 1 for every electron 2 or more shells lower. Here's what I mean. How many other electrons are in the 5s orbital? 1. So we deduct 0.35 for that. We deduct 0.85 for every electron 1 shell lower. That's the 4th shell, and there's only 8 electrons there. So we deduct 0.85 8 times, and we subtract 1 for every electron 2 or more shells lower. That's the 3rd shell or lower. So we're going to subtract 10 for these, 8 for all these, 8 for all these, and 2 for all those. These are all the amounts of shielding that each electron contributes. We got to add them all up. 2 and 8 and 8 and 10 and 8 times 0.85 and 1 times 0.35. Add all those up, you get 35.15. So the effective nuclear charge on the 5s electron in SR is atomic number of SR minus this shielding. When you do that, you end up with 2.85. Wow, a 5s electron hardly sees anything of the center. I guess that makes sense because it's so far away and there's all these other electrons blocking its view. Now, the only exception ever to these rules that I've proposed to you is if you're asked for the effective nuclear charge of a 1s electron, the total shielding is just 0.3. Here's what I mean. If you want the effective nuclear charge for a 1s electron in neodymium, doesn't matter what this is, could have been americium or, I don't know, californium, whatever. None of the electrons in shells farther than the 1s are going to count because they're outside and they're not blocking the 1s electron's view of the nucleus. The only thing blocking a 1s electron's view of the nucleus is the other 1s electron. And that other 1s electron always contributes 0.3. So the effective nuclear charge for neodymium, a 1s electron in neodymium I should say, is 60 atomic number minus the total shielding, 59.7.